In this section, we will consider the application of students' t-distribution for testing dependent samples. The test is also known as t-test for paired observations. Here we consider a set of variables given in pairs, that is x1, y1, x2, y2, etc., xn, yn. Here, the first element of the pair represents the variables of the units representing the sample before the units undergoing certain treatment, and y1, y2, etc., yn represent this reading from the same units after they undergo certain treatment. So this test can be considered in the case of whether a training program was of useful or not. So if you consider some n children, then x1, x2, etc., xn represents the scores obtained by these young children before they undergo certain training program. And after the training program, we again conduct a test, and y1, y2, etc., yn represents the scores after the training program. Since same unit was undergoing investigation in two phases, the samples are said to be dependent sample, or the observations will be in the form of pairs. So we consider a similar example, that is to application of students t-distribution for independent samples, that is for equality of means of two independent normal populations, that is h0 mu1 equal to mu2, and in that case the two populations are independent, that is h0 mu1 equal to mu2 when the population mu1 equal to mu2 when the populations are independent. But in this present test for dependent sample, the observations are undergoing investigation in two phases. One is before certain treatment, before applying some treatment, and second is after undergoing a treatment. That's why we have the observations in pairs. Now, suppose x1, y1, x2, y2, etc., x and yn are the pairs obtained, or xi, yi is the observation from the ith unit of investigation before and after this treatment. Now we have considered a population known as the difference population by considering the differences of the readings, and it is denoted by di. Di is equal to xi minus yi. I is equal to 1, 2, 3, etc. n. So we always keep the order, the first element of the pair minus the second element of the pair, and therefore if h0 mu1 equal to mu2 is the real null hypothesis, is the exact null hypothesis, we can take it as a hypothesis h0 mu d equal to 0. What is mu d then? Mu d is the mean of the differences, that is mu1 equal to mu2 is now mu d equal to 0. The mu d represents the mean of the entire differences considered in the population. Now this d1, d2, etc., dn obtained for the samples x1, x1, y1, x2, y2, etc., xn, yn can be considered as a sample drawn from the population with h0 mu d equal to 0. Therefore, this h0 mu d equal to 0 can be considered as case of testing mean of a population has a specified value, and for that we have the test t equals x bar minus mu 0 into root n minus 1 by s. This is the test statistic for testing mean of a normal population has a specified value. Here x bar will be replaced by d bar, mu 0 will be replaced by 0, root n minus 1 as same, and s will be taken as sd, that s suffix d. The suffix d is written to show that it is the standard deviation of the differences. Therefore, the test statistic is t is equal to d bar root n minus 1 divided by sd. Here d bar is the mean of the differences of the pairs given in the sample, n is the sample size, and sd is the standard deviation of the differences, that is d1, d2, etc., dn. S suffix d is to show that It is the standard deviation of the differences. And we have the equations of d bar and sd. D bar is 1 by n sigma is equal to 1 to n di, and sd is 1 by n sigma is equal to 1 to n di square minus 1 by n sigma is equal to 1 to n di the whole square. Here di represents the difference of xi and yi, and we keep the order xi minus yi always. Now, the critical region for corresponding to various alternative hypotheses are as before, are just discussed in the case of the mean of a population, mean of a normal population has a specified value. So if alpha is the significance level and if h0 mu greater than 0, this is not actually mu, this is mu d greater than 0, the right side test, the reject the null hypothesis if the calculated value of the test statistic is greater than the table value T alpha. T alpha we can obtain from tables of student state distribution, that is for degrees of freedom n minus 1 and alpha one-sided, that is if alpha is 0.05 we have to refer to the 0.05 given in the lower row. And likewise, if the test is left-sided, then the critical region will be T less than minus T alpha, and T alpha as before, referred as before. Now, if the test is two-sided, then we have this H1 mu D. This is not mu, it is actually mu D. Mu D not equal to 0, and then the critical region is modulus T greater than or equal to T alpha by 2. That is T less than or equal to minus T alpha by 2 or greater than or equal to T alpha by 2. T alpha by 2 from the tables of T distribution. It is the coincidence of the degrees of freedom n minus 1 and probability alpha two-sided or alpha by 2 one-sided. The alpha two-sided values are given in the upper row, that is 0.05 in the upper row, and alpha by 2 one-sided, that is 0.025. So in the lower row, that is alpha two-sided and alpha by 2 one-sided are recorded in same column. So thus the critical region for testing h0 mu d equal to 0 and h1 mu d not equal to 0 is modulus t greater than or equal to t alpha by 2. That's it. So that's about t distribution test for dependent samples.